as I was saying to Maciej, I will continue on my phone because I have to go home. I will listen in from my phone, but Andrea will do the moderation for the questions. He's just next to me here.
I'll keep track of the time so that 5 p.m. We wrap up.
Am I good to go, Andrea?
Just a moment, Maciej. So we are live on YouTube and it's recording on the cloud. Okay, so we are. Thank you, Maciej, for accepting the invitation today for the QISS seminar from the Department of Applied Mathematics and Theoretical Physics of the University of Cambridge. Maciej Dunajski, I hope I'm pronouncing it well, or not too bad at least. And today's talk is on the quantum state reduction and Newtonian twistor theory. Maciej, whenever you're ready.
Thank you, Marius. Thank you, Andrea. Thank you for the invitation and the introduction. I can't really say it's a pleasure to be here because I don't know where you guys are, but you know, these are the times. I'll talk about you know, several ideas which build upon Roger Penrose's 30 or 40 years thinking about quantum mechanics and potentially its connection with TwisterFiori. So that the background which I'm going to tell you about is Roger's ideas on the role of gravity, classical gravity, that is in quantum state reductions. The two papers I list first, the more recent one on gravitization in quantum mechanics. As you'll see, the proposal I'm going to put in front of you will connect these ideas with a certain limit of TwisterFiori. This is a limit where the speed of light becomes infinite, and this is something I've developed with my research student James Gundry, 5-6 years ago. But most of what I'll speak about today is in the paper I wrote with Roger. We put it on arXiv about 2 months ago. And I'm told it should be brief, at least the top part, and not technical. And you know, I don't know what your style is, but do interrupt me, ask questions. I'm going to start off reviewing what, you know, quantum mechanics as Penrose understands it and promotes it. And you know, myself, I'm to some extent, well, not an expert on financialized issues of quantum mechanics, and I'm agnostic about some of these ideas, and you might well agree with them or disagree with them, but I list them in order because that's my starting point. You know, that's what you have to take for granted in order to accept the rest I'm going to say. So in Roger's way of thinking of quantum mechanics, quantum evolution takes place at 2 levels. There is the unitary holomorphic evolution governed by the Schrödinger equation, and that's referred to as the U process. And I think on this U process part, Roger would agree with most other thinkers, researchers in quantum theory. And then there is another kind of process, which he refers to as the R process. R stands for reduction, which describes the wave function collapse. And at the level of formalism of quantum mechanics, that one is not holomorphic. For example, because you need to take complex conjugates of the wave function in order to calculate the probability amplitudes of finding something in one state or other. Now, in this approach, the R process is taken to be we will take it to be a real process taking place in time. So it's not instantaneous, it takes time. And Penrose argues that in order to understand how this process works, gravitational effects need to be taken into account. And then once they are, then the U process and the R process will both follow from perhaps some bigger, as yet unknown theory. And the idea here is to gravitize quantum mechanics rather than quantize gravity. So, we're not going to do what the mainstream, I guess, physics is occupied with, which is taking a classical gravity and trying to quantize it, or another approach taking some bigger theory like that of strings and seeing how gravity arises as the low energy limit of it. We are actually taking classical gravity as the holy grail, and we're going to, to modify quantum mechanics. We're proposing that it needs to be modified in order to account for this RU dichotomy. Now, what is this talk going to be about? As you'll see, one of the entry points to this role of gravity in quantum state reduction is trying to combine the principle of equivalence with gravity. And it's been argued by many, including Roger, that if you take the principle of equivalence seriously, then at least at the level of uniform gravitational field, there is a phase ambiguity in the wave function, which is nonlinear in time and therefore causes some problems. And we will show that this phase ambiguity is not an artifact of using a uniform gravitational field, but it's in fact robust. This argument only requires a Newtonian gravity framework. So we're going to incorporate a non-standard description of Newtonian gravity, that is the non-relativistic TwisterFiori. And this version of TwisterFiori, unlike the better non-relativistic ones, this describes all Newtonian spacetimes in a non-local way. So in TwisterFiori, one of the features of the TwisterFiori is that spacetime point or event is not to be taken as fundamental, but it's a derived object. Okay, so this quantum non-locality of the R process will be combined with the twistor non-locality into a proposal, which I should say at the start is a speculative proposal for a twistor description of the wave function collapse. And I'll try to be as honest as I can, and I tell you where the kind of firm mathematics or science ends and maybe some speculation starts. Right, well, let's start off with a Schrödinger equation for a particle moving in a uniform gravitational field. We can think of this as the gravitational field of the Earth. And the way we're going to incorporate it is by taking the potential in the Schrödinger equation to be that Newtonian potential, where this bold letter G is the constant vector of gravity. Right, we have a choice here. See, we can describe this process in the Newtonian frame, where there is a potential, or we can, in accordance with Einstein's principle of equivalence, go to the accelerating frame, and this is a frame of the falling object. Now, how do you do that? Well, you find a transformation between the Newtonian and the accelerating frame, and then you find, and at this level it's a chain rule calculation, is that in the accelerating frame where there is no potential, there is a capital psi, which solves the time-dependent Schrödinger equation with no potential. And this capital psi is related to little psi I've had before by a phase transformation. And this phase transformation contains a cubic time dependence. Now, this, you can think of this as the non-relativistic artifact of the Unruh effect, which applies for finite speed of light. And Unruh pointed out that depending on the observer, there is an ambiguity in what is to be taken as positive and negative frequency decomposition, and this ambiguity gave rise to the ambiguity in the definition of a particle number, which then led to what we now call the Unruh and effectively Hawking temperature. So there is a calculation which I'm going to skip, which shows that this phase ambiguity at the level of Schrödinger equation is a limit of the Unruh effect. Now, why is it a problem? See, it's not considered to, the Unruh effect is not considered to be a problem in a conventional quantum field theory, because although different observers will detect different numbers of particles, you have to choose what sort of frame you want to be calculating with, the accelerating observer or not, and stick to this frame and you will be all right. But the problem comes if you want to talk about superposition of massive objects. So imagine, rather than a particle in the gravitational field of the Earth, imagine two particles with masses, imagine one particle with mass, and this particle enters some quantum superposition state with itself, and then there is a gravitational self-interaction between this passive object and its superposed object, and you don't have a preferred frame to work with. You have to work in this accelerating Einstein frame connected to one or the other, but then you find yourself having two different Hilbert spaces associated to these two superposed spaces, in each of its own notion of stationary state and its own wave function, which the standard rules of quantum mechanics do not apply. Now you might say, is it, to what extent is it a realistic scenario? Well, Andrea and Marius told me they're based in Vienna. When I started as a PhD student at Oxford, I met a young postdoc who just came back from Vienna, where he was doing experiments with Anton Zeilinger. His name is David Baudmister, and he, following conversations with Roger, got involved in creating an experiment which can detect the time of the wave function collapse of such superposed objects. And it's been good 25 years now, and this experiment, as I understand, is still being prepared. Now, I'll move away, sadly, from experiments, but also from the uniform field. So I want to show you that this cubic in time ambiguity is not an artifact of using the uniform field, but it's actually there for any gravitational field, any Newtonian gravitational field. And here's a piece of formalism I'm going to use here, known as the Eisenhower metric. And what you do is you consider what we call a plane wave metric. It's in 5 dimensions. So 5 coordinates, the x's and the t, these are the physical coordinates, plus an additional coordinate I'm going to call u. And you write down this metric. It involves a function, v. Now, it is an observation of Eisenhower, although in the modern era it was discovered, maybe rediscovered in Marseille by Christian Duval and his students and colleagues, and Christians really made great contributions out of it. But it does go back to Eisenhower, mid-1920s, that null geodesics of this plane wave metric project down under this null Kaluza-Klein reduction by a null vector d by du. They project down to trajectories of a Newtonian particle. So here is a way, one of a few ways of understanding Newtonian physics as coming from geodesic motion of some metric. But you have to look at this metric in plane wave in 1 dimension higher. What's relevant for us is that there is also a way of incorporating quantum physics into this picture. Well, what you do there is you take a wave operator of this metric G and the kernel of this operator, and you make an ansatz. You say that phi is of the form e to the minus I mu over h bar, where u is this null coordinate, times some function of x and t. And then there is a calculation, which requires you to know this wave operator, to show that the wave equation on phi reduces down to the Schrödinger equation on psi. Now, what is it good for in our context? Well, you see, let's say that we take this potential in the Eisenhower metric to be the Newtonian potential. Then a calculation of the curvature of the Eisenhower metric shows you that it's flat. It's flat, but with this v, it's not written in flat coordinates. One of the results, and some would say definition of flatness, is that there exist flat coordinates. So you could find them for the Eisenhower metric by the capital U, capital T, and capital X. Now, if I give it explicitly here, you can now, instead of looking at this wave operator in the Newtonian coordinates, you look at them in the flat coordinates. Well, there the wave operator is just the flat wave operator, and the resulting Schrödinger equation is the free Schrödinger equation. But you see, you can do it very explicitly here with no, because you just write one wave function either in the Newtonian coordinates or the flat coordinates. There is a nonlinear term in the transformation between the u directions, and that contributes to the phase. And that's precisely the phase ambiguity I told you about here on the first slide, which relates to reference frames. So this, so far this Eisenhower metric gives us a sleek way of relating two coordinate systems.
So Maciej, when you say flat coordinates, maybe, I mean, the metric is flat in any coordinates, but maybe you mean something like Cartesian coordinates.
Yes, the definition, it's not Cartesian because the metric is not Euclidean, it's Lorentzian. The flat coordinates, is to me are the coordinates where the metric, the quadratic form given by the metric is just a constant matrix. So the flat coordinates is ut and x. The quadratic form which goes with it is a constant matrix.
Okay, fine. Thanks.
Yeah, good. Okay. So, these flat coordinates, they only exist, or they always exist at the point. I mean, it's fact of life in mathematics that you can, there is a comment. It means metric tensor is the same at all points. That is correct. Yes, that is correct. Thank you. So, you can construct these flat coordinates at any point, and that means that you can kill off Christoffel symbols at any point, so kill off accelerations at any point, but you cannot, extend these flat coordinates into a neighborhood of a point if the curvature is not zero. So what's the next best thing? Well, it's what people call normal coordinates, and among all these normal coordinate types, there are special ones, which we call Riemann coordinates, and they distinguish from other normal coordinate systems, not only by the fact, well, it's not only the case in these coordinates, you see that the Christoffel symbols, the accelerations vanish at the point where the system is centered. It's also the case that the quadratic term in the metric is given by the Riemann tensor, right? So we don't have, for non-uniform gravitational fields, we don't have the notion of flat coordinates, so the Einstein accelerating frame, but we're going to replace it by this Riemann coordinates. So now the point of the exercise is to take this Eisenhower metric and construct the Riemann coordinates for them. The capital X here corresponds to u, x, t, and xi's. And here is an explicit transformation to the Riemann coordinates. And now you again take something in the kernel of the wave operator, make this ansatz, which reduces the wave operator to the Schrödinger operator, and observe that because of this cubic time dependence in the translation of this null coordinate u, there will be also a phase ambiguity between the two wave functions in Schrödinger frames, one corresponding to Newtonian coordinates and another one to these Riemann coordinates. And the term multiplying this cubic in time dependence, the gamma term, is, technically speaking, these are components of what's called Newton-Cartan connection, but it doesn't matter what they called, what they are. What does matter, though, is that this T-cube term is robust. It's not only an artifact of taking a uniform gravitational field. So then, that's the first part of my talk, this observation. The second part will bring in TwisterFiori. So, TwisterFiori started off as a theory of physics, non-local theory of space and time, which takes a view that light rays are more fundamental than events. So in TwisterFiori, the events are derived objects and the light rays are fundamental. And it gives a non-perturbative description of parts of physics, but suddenly it's, so it describes special relativity very well, and everything must as conformal, but it's constrained by a technical notion of self-duality. So for technical reasons, I'm not going to go into. TwisterFiori does not incorporate full Einstein's equations in Lorentzian or even in Riemannian signature, but only half of the degrees of freedom. So in that way, it deviates from physics a bit, but it had a huge impact, positive impact on pure mathematics, ranging from differential geometry and integrability. Back in the day, when one could still organize conferences in person, and where people were willing to come to these conferences, Simone and I organized one in Marseille. We brought physicists together and geometers, and they are supposed to talk to each other and exchange ideas. But as you would expect, the physicists talk to physicists, the geometers talk to geometers, and then we parted, and then COVID prevented us from having any more meetings of this.
But we enjoyed very much the Calonchi nonetheless.
We did enjoy the event very much. Now, there is a version of TwisterFiori which removes this self-duality constraint, and it describes physics as we know it in the Newtonian limit. And the kind of mathematical feature of this non-relativistic limit of TwisterFiori is a phenomenon in algebraic geometry known as the jumping line. So in TwisterFiori, space-time points, events correspond to holomorphic curves of CP1s, which are submanifolds of the twistor space, which itself is some complex threefold. What happens in algebraic geometry, the holomorphic type of these lines is described by their normal bundle. What's the most, curious so results of this non-relativistic limit is that in that limit, the holomorphic types of these curves jumps from one type to another, which makes this Newtonian TwisterFiori unstable under holomorphic deformations. We don't know what it means really physically, although we understand the maths. It describes all Newtonian spacetimes, and you can understand all the Newtonian connections, interactions by taking some limits of gravitational instances. So, it's quite a sound theory.
Sorry, can you characterize this, what do you mean by Newtonian spacetimes in terms of the Weil tensor?
Well, sorry, by Newtonian spacetimes, I just mean non-relative, what people call Newton-Cartan theory. So a theory where you have a potential and you have a time simultaneity and you have some notion of freefall. I'm going to get there in a moment. So I tell you what Newtonian spacetimes are.
Okay, I'm specifically interested in knowing what the Weil tensor is, if it's zero or not zero, or in order to understand.
The Weil tensor of the curvature of the Newtonian connection is non-zero.
I see.
Okay, right. So now that's the kind of technical slide. So bear with me. Maybe we'll get something out of it, but it illustrates this kind of limit in the essence. So I'm assuming you don't know anything about TwisterFiori. I'm declaring a twistor space, or really a one-parameter family of twistor spaces parameterized by C, to be a complex threefold covered by two open sets with the following patching relations. The way we describe manifolds is by patching. Now, it's, this complex threefold is a vector bundle over a projective line with some patching matrix. And you find by analyzing this patching matrix that if the C, which will be the speed of light, if that's infinity, if that's not infinity, then the twistor space is the standard Penrosian twistor space, but in the limit where C becomes infinite, it has a different holomorphic type. I'm not going to go into descriptions of these symbols. That means that the normal bundle to twistor curves are different. So you have this kind of family of twistor spaces with this branching. Now, what's the space-time in this language? It's a space of lines, space of holomorphic lines in the twistor space. It's four-dimensional, so we have four-dimensional family of curves. So I'm telling you how Q and T depend on lambda, but there are four parameters, X, Y, Z, and T, which enters into this discussion. And these X, Y, Z, and T are coordinates on space-time. You see, if the speed of light is not infinite, then you say the 2 points are now separated if the corresponding lines intersect at one point. And then the calculation will give you an expression for a conformal structure on this space of lines. On the other hand, if C is infinite, then you find that this twistor space admits a global twistor function, and that leads to a concept of simultaneity on space. So how does that work? Well, that's this essence of Newton-Cartan theory. What's a Newtonian spacetime? It consists of a triple, a connection, a degenerate metric, and the one form. And you see the one form, theta, it's parallel with respect to connection. So it gives you, it gives you a notion of time function and a vibration of Newtonian space-time all over the time axis. So you have the time simultaneity. This metric H is the inverse metric on the fibers of the vibration. So it makes sense in Newtonian theory to say how far are 2 points, assuming that these are points at the same time. But there is no metric in this theory connecting different points, different events at different times. And that needs a connection, which then tells us, what the trajectories of Newtonian particles are. And this connection has to be such that it preserves this metric and the one. So that's what I mean by the Newtonian spacetime. And this connection has a Wald tensor and it doesn't have to be zero. So free fall is described by the geodesics of this connection, the time simultaneity by some vibration over the time axis. I should say, although there is an absolute notion of time, there is no absolute notion of space. That needs some choice of Galilean coordinates, but we will not need that. There is a way of getting, so I told you how to get the metric and the simultaneity from the twistor space. I didn't tell you how you get the connection. Well, there is a way to do it. Again, that's the kind of above the level of technicalities I should be getting into. But you take a one parameter family of gravitational instantons, which we know are described by TwisterFiori. These are Ricci flat if V and A satisfy this monopole equation. So V is a harmonic function. I've written it in a fairly non-standard form, which depends on the parameter epsilon. Epsilon is 1 over c squared. So that it has a twistor description given by some deformation, but it also has a Newtonian limit. In this limit, the metric blows up, the limit where c goes to infinity or epsilon becomes 0. But the Levi-Civita, the Christoffel symbols survive, and they are given by a gradient of a function which you then construct twistorially. So there is a twistor procedure of how you arrive in the limit at this Newtonian connection, the last ingredient of what we needed for a Newtonian twistor theory. Now, so up to now, what I've told you is still firm, and I can answer any questions about it if you will have any. And now I'm going to a proposal, fairly speculative proposal, and I'm unlikely to be able to answer many questions about it. And in fact, the more sensible question you ask, the less likely I am to answer it. But there is some merit in it, and some maths. So here it goes. What's the proposal for twistor wave function collapse? We're going to assume that the reduction process, the R process, takes place between two measurements at T0 and T1. So it takes place in time. The first measure brings a discontinuous jumping to the space-time structure, so brings enough gravity to deform the twistor space. Now, this part is actually firm that we know that these non-relativistic twistor spaces are unstable under codiral deformations of curves. So we'll jump back into relativistic twistor spaces. And we're proposing that that will happen for some cohomology class. And then, although the space-time, the family of curves, so the space-time might disappear in the measurement process, needs to be replaced by a new family of curves, a new space-time, something drastic happens. The twistor space, we claim, survives the reduction, so the twistor space stays, but the 4-parameter family of lines with some normal bundle needs to be replaced by another such family. So this kind of proposal is illustrated on this diagram where you have two non-relativistic twistor spaces with curves of normal bundle O plus O2, and they, so in the measurement process, they are replaced for some time by a family of curves with different normal bundle corresponding to gravitational effect in the wave function collapse. So that's it. That's it for the kind of formal part of my talk. I'll invite questions if there are any.
Yeah, I think it would be nice to elaborate more. Sorry.
Yes, you want to? No, I was going to say just thank Maciej, and I was going to open for questions, but okay. You can.
Well, maybe you can. We think.
You can go.
Yeah, because it went fast, this final part, no? So maybe elaborating a bit more on. So, okay, you gave us the mathematical background that you're going to use, but then you went into discussing some very special and important physical phenomena, which is the one of the collapse. And so, are we supposed to understand that? So the process of the collapse, you say, is described by that intermediate slice in which twistor space behaves relativistically.
It's the curves in the twistor space. The twistor space stays as a manifold, but the curves in twistor space have different holomorphic type, which is this marker of relativity. Yes. But I'm observing, so can you say more about what is the meaning of the importance of the Newtonian description? So you have been stressing that it's important to take the non-relativistic limit in order to give this description. Can you? Yes. Okay. The importance of Newtonian description is twofold, and it's in both cases approximate. First of all, TwisterFiori, as we know it, doesn't deal with relativity in the relativistic description, doesn't deal with Einstein's equations, because in Lorentzian signature you cannot have curved metrics twistorially, right? So we want to bring TwisterFiori to physics, to real gravitational physics as we know it. Sadly, we cannot do it yet. Maybe we will never be able to in ordinary TwisterFiori. On the other hand, all Newtonian spacetimes are described in an honest way by these twistor spaces I told you about. So if you have the opinion, as Roger is, that this gravitational effect in quantum mechanics is already present at Newtonian level, you might just stick to the Newtonian level, okay? And so that's the justification of why Newtonian TwisterFiori. Now, one Newtonian physics in quantum mechanics, well, that's because of this phase ambiguity picture on my second slide, which only needed Newtonian potential and Newtonian physics.
Right, but because you stress that you go through the relativistic description in these intermediate slides, maybe that is what is confusing. So even though you describe prior and after the gravitational interaction, the Newtonian space using just the non-relativistic limit, am I understanding correctly that the collapse itself involves the relativistic description?
In the proposal, the collapse itself involves, gravitational effect on space-time, which at the level of TwisterFiori corresponds to a deformation of a complex structure of twistor space.
Right.
That's Penrosian way of doing it. Now, it is the case, that's what I proved with this guy Gundry, is that these deformations, holomorphic deformations of twistor spaces, make the Newtonian twistor space unstable. It jumps into relativistic realm. So that's what happens. So, but that's some effect on the space-time. So non-relativistic space-time dies, and for this time of the wave function collapse, relativistic effects have to be taken into account. But at the twistor level, and that that may be the punchline of this proposal. At the twistor level, it's less drastic than the space-time level, because although the notion of space-time ends, the twistor space survive. Now you might say, what do you mean by the saying that notion of space-time ends? Well, no, if you into Everett many world interpretation, then that's what, that's a very drastic thing on the space-time, that it branches, and each possibility of a quantum measurement takes place in its own space-time. So, if you call that drastic, and I certainly would, then the twistorial chaotic holomorphic types of curves is supposed to be less drastic. There is a question from chat. The wave functions collapse to eigenstates. Can you elaborate on what in the formalism picks the eigenstate? No, it's one of the very good questions which are out there, and I cannot answer. So we have no control of these eigenstates. So we cannot say why a wave function collapses to one eigenstate, not the other.
But do you have a way to know if it collapses, at least in the position eigenbasis? Like no, the basis problem even?
No, we don't.
There are other questions. You can either raise your hand in the chat or unmute yourself. I see Nick Haggett.
Hi, yeah, no, thanks for that. Thanks for the talk. I mean, I think I still have some questions about at the end, but I wanted to ask about something earlier on. So, about the phase ambiguity that occurs in the phase ambiguity you were talking about at the beginning, yes, in a constant gravitational field. So, I mean, I'm thinking about the sort of 1970s and sort of neutron interferometry experiments, the cow experiments. Why don't they sort of settle the ambiguity question there? I mean, how does that interact with those experiments?
Are these the experiments which there are three names associated to these experiments? One of them is Corella.
Yeah.
Overhauser. Very good. So these experiments, as I understand them, confirm that there is nothing wrong with equivalence principle in quantum mechanics. And because they refer to gravitational field of the Earth, and all you need to do is you pick one reference frame or the other, and quantum mechanics is consistent. But in Roger's way of thinking about wave function collapse, which kicks in here, this ambiguity applies where one massive quantum state is superposed with itself, right? So you don't have some background gravitational field like that of the Earth, and you choose to work in one frame or the other, either the Earth frame or the free-falling frame, but you have a superposition of two gravitational bodies, and each of these gravitational bodies has its own Schrödinger equation and phase and Hilbert space. So there it really becomes an issue.
Okay. So you're saying it's because in the cow experiments, you do have a superposition of massive objects, but they're not the source of the gravitational field.
That's absolutely correct.
The source. Okay. All right. So it is like what people are talking about now, the gravitationally induced entanglement experiments. These are new. Yeah. Okay.
Yeah.
That people want to do. Okay. Very good. Thank you. Well, if nobody else, I'll go again. If people, no, go.
Please do, please do.
So yeah, okay. So this was back to the end of the talk again, and maybe this is Penrose's law again. But I mean, usually collapses don't require two measurements. Can you talk a bit about, you know, why the thinking behind collapse being something that happens, yeah, between two measurements rather than just when you have one measurement?
So what that is, perhaps this is my, I should declare myself as a newcomer in the world of measurements and the terminology which goes with it. My understanding, which you might say is just invalid, is that measurement, you know, measurement is something which takes place in time. So you can say that there is a beginning of the measurement and the end of the measurement. So that is what I referred to as this T0 and T1.
Okay, sorry, I thought at one point there was one measurement and then another one, but this is a sort of finite extent of measurement. Do you have some way of characterizing, you know, what a measurement is, or that's just sort of put in, that is kind of put in by hand? Or is a measurement anything which, you know, actually has this effect on twistor space, really?
Well, that would be a twistorial. That would good. Okay, that would be a twistorial working definition of a measurement in the context of Newtonian twistor theory. Is that an effect which brings in, you know, enough. So there is a well-defined way how you turn the kind of gravitational interaction, any gravitational effect on space-time into a deformation of a twistor space. This sits hidden in this function f, the cohomology. So, but in this case, this particular type of deformation destroys the types of twistor space, makes them jump. So one could define measurement in this context as any effect which has this consequence of twistor curves.
Very naive question, but so am I then to somehow still think of the measurement as some non-unitary process in which this non-unitarity is somehow related to the change of complex, to the non-preservation of the complex structure in the twistor space description, or something will change at that level?
No, I don't think I mean, that's a fault, but I don't think we're saying that we're not going that far. So Roger has never really proposed what this big theory should be, which replaces the U process and the R process, whether it should be unitary or not. I mean, he might have a view on that, but we're not proposing any deviation from unitarity here. So the complex, that's a good point. The complex structure, well, the complex structure of the twistor space changes because I deform it. But how it relates to the unitarity of quantum evolution, I don't know. I mean, you know, measurement is considered to be non-unitary. Right.
So that's why I was thinking. So the naive expectation would be, so in this description, it still stays non-unitary. It's just that the non-unitarity now is explained in terms of this non-preservation of the complex structure. Correct. Or maybe there's no relation whatsoever, and then this description might lead you to a unitary description of the collapse. So this is what I was wondering.
Perhaps.
Okay, I see. It's open. Okay, thank you. And any concerning, you know, the Diossi experiments and those things, any?
Well, yeah, okay. So I was, you know, so I don't know about Diossi experiments, but I know about this Dick Bovmister experiment. Remember, he talked at our conference, and he puts some, you know, crystal in a quantum superposition with itself, and it requires some super precise mirrors, and it all you know, so okay, so the bit which I didn't talk about, which forms part of Penrose's theory, is that it predicts the time the measurement takes, so time of collapse of the wave function, and this time is related to the kind of self-gravitating energy of these quantum superpositions by time energy Heisenberg uncertainty. So essentially, time of the collapse is the self-gravitational energy divided by the Planck constant. And that's what this experiment is apparently going to measure. So it's supposed to be measurable time. But you know, I mean, there are some technology barriers. I'm in touch with Dirk every few years, and I ask him, and he says it's 5 years away. But you know, the number 5 doesn't seem to change that much. But it's, you know, it's not some. What I can say with some, it's not some science fiction sort of wishful thinking. They really are working with these crystals and technologies trying to make that happen. Now, it'll be great if it could happen anytime soon.
No, but I mean, okay, but this approach you're developing here does not change the structure of the experiment, does not change the bounds on time and the relation with the self-energy.
No, it doesn't.
Right, okay.
It kind of tries to bring a very early version of a theory which would explain the results of this experiment.
But without changing the time relation to the
right.
self-energy. Okay, thank you very much.
Are there any other questions? I remind the audience that Maciej has to go at 5 p.m. So this was your last chance. So while we wait, I have another question. So at one point, you mentioned that the twistor theory has limits the description of the self-dual part of the space-time. So this is my ignorance about the subject, but I wanted to understand, like, what's in the talk, where is that that you take a turn away from established general relativity, and because of this where this constraint
this concept of self-duality, that's a property of the Wald tensor. So, you know, Wald tensor is self-dual if you're used to this kind of language notation. If you raise a couple of its indices using the volume form and you guess plus or minus the Wald tensor. And it's only those which TwisterFiori describes for reasons which I can explain. But it's worse than that, because this it only describes self-dual things, but one can show quite easily that the non-trivial, non-conformally flat space-time which are self-dual cannot exist in Lorentzian signature. So a self-dual space-time is necessarily Riemannian, or it has 2 times and 2 space directions. Now, where can I rescue myself from this? Well, that is, I think, a good point it's here. I have a self-dual space-time. It's self-dual because V and A satisfy this equation, and it's Riemannian, okay? And it has its twistor space for MEV and MEA subject to this relation. But then there is this epsilon, which is 1 over c squared. And I'm telling you, there is a way of taking a limit of this self-dual space-time, where in that limit, you're going to get the Newtonian connection of this form, but this is precisely the sort of connection which describes all Newtonian physics, because having this Newtonian connection is just a way of saying that, that Newtonian trajectories, mx double dot equals minus gradient of v, that they are geodesics of this connection, but we've got it here. So it's by taking this limit, we freed ourselves from the concept of self-duality and Lorentzian and Riemannian signature.
Because you even don't see anymore the distinction between Lorentzian and Euclidean.
Exactly, and that's exactly right, and that's the key point, that at Newtonian level there isn't one, because it's changing between Lorentzian and Riemannian is like changing x to minus x, and you can change the equations are second order in time, but the overall sign can be massaged. So rather than taking t goes to it, I can take v goes to minus v, or x goes to minus x. Not a big deal.
And since you mentioned Christian Duval, how about the other limit that he also worked on? The Carolian limit, C going to 0.
I don't know. I mean, someone emailed me that recently. Maybe this person wasn't in the audience. It was a good question. What is the Carolian limit of twistor space? That's where the C goes to 0. I don't know what that is.
Okay, so more work to be done there then. Okay, thank you.
Thank you.
So are there any other questions? So it looks like, Maciej, you'll have more time to find your keys.
That's my ID.
Your ID, your ID.
I wish it was keys. Keys are easy. ID is bad. Well, thank you very much, guys. And I hope to see you in real life sometime soon.
Yes, same wise. Bye-bye.